Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Alex Demarcus. He is an assistant professor at the Viterbi School of Engineering at USC. Before that, he was a postdoc at Caltech, and before that, a graduate student at UC Berkeley. And during that time, he was an MSR graduate fellow here, so it's a great pleasure for me to welcome him back to MSR. Alex?
Thanks, Phil. So it's great to be back in the new building. So I will talk about network coding for distributed storage. And before I talk about network coding, I want to talk about coding. So how to store information using erasure codes. So this is a very basic slide, but very useful for anything else that follows. So let's say you have a file or a data object, which is this big yellow box here. And you cut it into two pieces. So K is going to be 2 in these examples. And you can use a code, a 3,2 code, to store information distributedly. So the way you store is you store the first packet, the first part of the file in one server, the second part in another server, and you store the bitwise XOR of the packets in a third server. And this is just a single parity disk, and this is used all over the place, of course. And the key point here is that you have generated 3 packets that, so that any 2 out of the 3 allow you to recover the original 2. So that's why this is a 3,2 maximum distance separable code, and it's also known as a single parity. This is a little more interesting case where I generate 4 packets. This is a single parity. And this is A plus 2B. A plus 2B, what does that mean? It means that I group my bits into groups of 2, let's say. I think of them as numbers in a larger finite field. And then I do my operations in a larger finite field. If you don't know about finite fields, then you can just think of these as linear equations over the reals, and everything will work out fine. The key point here is that these are 4 linear equations, and any 2 out of these 4 allow me to reconstruct back A and B. For example, if I get B and A plus 2B, these are 2 linear equations I can use to get back A and B. Okay. The point of this slide is that erasure codes are better than replication. So what is replication? Replication says, OK, just store your packet twice and store the other packet twice. And this is in 4 disks. And let's compare this with a 4,2 erasure code, which is the one I just showed. And what I want to say here is that this scheme here, the code, is much better than replication because to the right, any 2 allow us to recover the file, whereas for this 2x replication scheme, if I lose the first and the third disk, I'm fine. But if I lose the 2 first disks, I have lost A, and therefore I have lost data. Okay? So this scheme is more reliable than replication, of course. Okay. So this is well known, and in fact, erasure codes are introducing redundancy in an optimal way. It's optimal because any K packets allow you to recover your file, and you could not hope to get your file back from any K minus 1 because you don't get enough bits. And that's why people use erasure codes like Reed-Solomon, fountain codes. These are error-correcting codes more generally, and they use them all over the place. Still, however, most peer-to-peer storage systems and most information stored in data centers today uses replication. So they make 3, 4 copies of the objects. And they don't use parities, or they don't mix information together instead. Now, why is that? So this guy, this is Claude Shannon, and he was in the phone company, and he basically, one of the main results that he showed is that when people were sending bits over noisy channels, they were observing that, okay, we can repeat the bits, therefore our rate goes down, but our probability of error reduces, right? And people thought that to reduce the probability of error, you have to reduce the rate, and so you have to repeat your symbol more and more times. And if you want your probability of error to go to 0, the useful things you would be sending over the total number of bits you would be sending would be a ratio that vanishes. So that's what people believed. But the breakthrough result and the change of thinking was that you don't actually have to have that. You can have arbitrarily small probability of error with a fixed rate, as long as you're below the capacity. So practically what I'm saying is that replication, which is a repetition code, is a terribly bad code, and every coding theorist knows that. But still, this is what we use in many distributed storage systems. And the question is, can we improve the efficiency? Of course, we use replication for other reasons too, for load balancing, for efficiency. But at least for archival storage, when the main bottleneck is you want reliability, then for those cases we should be using codes. And why don't we? Well, people have worked on using codes. There are many problems when you try to use codes over networks. And this is great because there are new open problems for people to look at. So let me show you a few of them. One is, when you have two servers, let's say, that have two packets A and B, and they want to create this very basic code here that is A, B, and A XOR B. Every time you send a packet over a network now, you have to pay a communication cost. Typically, these costs were not considered important because everything was happening centrally. But now when you have a network of computers and the network is the bottleneck, you want to minimize the communication that's happening in the network. So this is one problem, how to create codes that have the smallest number of edges or the smallest amount of information when they are created. The other issue, for example, is update complexity, that if I'm storing A on this disk and A plus B on this disk, the XOR, when one packet changes, that means I have to go to all the disks that are storing parities combined with that, and I have to change those. So graph theoretically, that's correlated to the degree of each packet, and I would like to make these degrees as small as possible. The problem is these degrees are in direct conflict with reliability. So what is the minimum update complexity that you can have if you want to tolerate, any n minus k failures, for example, is one question that has been addressed a little bit, but there's many open problems there too. The main open problem that I will talk about is this one here, where, okay, you had your code, so this was a 3,2 code, but now you have a failure, so you have to get a new disk, and you have to communicate some information to the new disk so that these two guys with the new guy form a good code again. So this is going to be called the code repair problem. And the repair communication is a new problem that has not been looked at before because there was no network in the picture. OK. So the story is this guy. This is Sean Rea. He was a PhD student at Berkeley. And he was building this system. Has anyone heard of this OpenDHT system? It is a distributed peer-to-peer storage system. And later, as I read, the Dynamo system that's used in Amazon is building on that, and many other systems are building on these ideas. It's a system where you store distributed information over the internet. And they used a lot of replication or coding. So I was the coding theory guy around, and we went for coffee, and we were talking, and they said, okay, there's all these amazing developments in coding theory. We can do very fast decoding, sparse graph codes, fountain codes, network coding, all that. So perhaps we could use any of that in this distributed storage system. And basically, after talking with him, I realized that the main problem or one of the most important problems is this repair issue. It's not decoding complexity or sparsity or any of these things. So here is an example. Let's say you have your file is 7 packets total, and you encode it into 14. So that means any 7 out of these 14 allow you to get your file back. So this is your original data object here, and these are parities, 7 parities. So any 7 packets out of these 14 will allow you to recover your file back, and each packet is 1 megabyte in size. Let's say the total file is 7. And they were using in OpenDHT, they were using Reed-Solomon codes or the information dispersal algorithm IDA, which is basically very similar. And when they had one failure, they had a new peer here that had to create a new parity. Or it's either a parity or X4, like the systematic symbol that was lost. The problem is that to create in a Reed-Solomon code, for example, to create a new parity, you need to have all the data. So to create one packet here that had size 1 megabyte, they had to send all these things to this guy. So that was 7 megabytes in communication over a network. And then this guy would use these, solve for all x1, x2, x3 up to x7, and then create the lost packet or a new linear combination here and store that. So this is the punchline, that the amount of network traffic required to reconstruct one lost data block was the main argument against using erasure codes in peer-to-peer storage systems. And several studies have pointed out that this is a big problem. And when you use codes as a black box, repairing one failure basically requires all the data to be present. Yes?
Do you have the same problem if some of your original data changes? So some of your XI changes?
Yeah, so if some of your XI changes, you have to go to all the parities and update them. So that's another problem. That's called the update complexity problem. That is, I mean, one way around this is say, okay, I'm never going to change things. I'm only going to use codes for stuff that is archival. So that's, typically this is the case of most interest. But there has been work on the update complexity. So it's a separate related problem. The B-codes, for example, have optimal update complexity. There are codes designed exactly for that issue. But for the repair problem, there was nothing. Yeah.
Although, if you consider archival, it's also true that usually archives are updated. So you append new
right.
files, right? You never change
sure.
things. So if you had things, you still require a lot of communication, right?
Yeah.
So you will have to update.
Yeah. Update is a separate problem that was known, and there is work. It's as far as I know, the optimal construction theoretically is a B-code that has minimal update complexity for a given reliability. So they use these in RAID 6, so this is a problem that's relevant even when the storage is centralized. The novelty in these problems is that when the storage is distributed, the network is the bottleneck, and now you have these also repair issues. But yeah, any other questions? Okay. So I will talk about this. The main problem is how do we repair a code? Well, one way to repair a code is bring all the data in one point, but you can do better than that. So this is setting up the problem more formally. Assume you have your code. Let's say it's a 4,2 MDS code, and the one node here, this guy leaves the system. The question is, how much data do we have to communicate to this guy, the newcomer, so that these 3 guys combined with the newcomer form a good n,k MDS code? So is the problem clear to everyone? Okay. Okay, first idea. Okay, definitely I can communicate 2 megabytes because any 2 megabytes out of this give me back all the data, as we said. So I can send 2 megabytes here. This guy can solve for A and B and store here A. Or could store a different linear combination, right? So it doesn't have to be A here. You could store A plus 50B As long as this is linearly independent from these, this is still a good code. OK. But the newcomer is going to download 2 megabytes and store only 1. Is it possible to download less? So this is a quote from a peer-to-peer storage paper that says if you use any of the codes we know, to make one packet, you need all the data. And the main point is that this is not always true. You don't always need all the data to make a new encoded packet. If you use network coding, you can do it with much less. So this is the main message of this talk. OK, so it is possible to download 1.5 megabyte. This is for this example. This is the information theoretic minimum. OK, how do you do it? The first thing you have to do is what's called sub-packetization. So you have to take every packet and cut it in 2. So check that this is a code that has 4 variables. Any 2 boxes now contain 4 linear equations in 4 variables, and you can check that you can actually solve these equations. So this is a 4,2 MDS code. Now when you have a failure, each guy is going to make a small linear combination of the 2 packets they have. Each packet here has size half a meg. So this is half a meg. So these are 3 packets of total size 1.5. You send these 3 packets to the newcomer. The newcomer makes a linear combination and stores it, and makes another linear combination and stores it here. And this is what is being stored. So you see what the scheme I'm suggesting is? One question now is, OK, instead of cutting it in 2 packets, why don't we cut it in 100 packets and send around 33 from each? And then the total communication would not be 1.5. The total communication would be approaching 1 megabyte as I cut smaller and smaller. Right? Well, if you do that, however, you can prove that this packet, these linear equations here, will not be good. They will not be in general position compared to these. So they will not form a good MDS code. So you can only reduce your communication to 1.5 in this example. So let me try to show you why this is the case. OK, so this is called the information flow graph. I take every storage node and I make 2 copies, and I connect them with one edge that is the capacity of the storage node. And here I put a source, a virtual source where all the data began. This is the newcomer. And the communication is going to be beta. This is to be minimized to repair this failure. Now, I want any 2 disks to contain enough information to recover the data. So I claim that if the minimum cut separating this source to this data collector is smaller than the file size, which is 2 megabytes in my example, it is information theoretically impossible to get the data here. So if you compute the minimum cut in this example, this is 1 cutting this edge plus 2 beta. And you find that 1 plus 2 beta has to be greater than 2 megabytes. So beta has to be greater than 1/2. So this is how you find that you could not communicate less than 1.5. But how do you actually achieve that, right? How is it possible to achieve? This is called a cut set lower bound. OK, the problem is, why is it not achievable? Because it's not only this pair of nodes that could fail. You want any pair of 2 nodes that fail to allow you to reconstruct the data. So you have to somehow simultaneously serve all the possible 4choose2 pairs that could appear. And this is here, after a lot of pain in PowerPoint, I added all the possible 4choose2 pairs. And now you want a code that simultaneously sends the data to all these guys. And how can we hope to do that? This is called multicasting in information theory. And the main message is that repairing a code is equivalent to multicasting on this graph that you can construct. And the breakthrough results of network coding, originally by Al-Suede et al., Keterin and Medar, and Tracy Ho, Medar, and co-workers, showed basically that if the minimum of the min cuts, so the minimum from the source to each one of these data collectors is sufficient, then there exists a code that sends the information to all of them simultaneously. This is highly non-trivial, right? Because I'm serving many people at the same time, and I'm serving everyone at the rate of the poorest. And further, you can achieve that with a linear code. And further, you don't even have to think too much about it. You can just make linear combinations of everything arriving. And with high probability, all these guys will get linear equations that will be solvable as long as you are not trying to communicate more than the min cut. So is it clear what I'm saying here? So the only thing we have to worry about if we're trying to repair our code is basically what is the right amount of information, and just random linear combinations will suffice. And you can, the thing you have to evaluate is the minimum cuts on these graphs that are formed by nodes failing. So if you have an n, k MDS code, if each node is storing alpha bits and communicates beta from each existing node, you can do the graph theory and find this is the storage, the minimum storage, and this is the communication required to repair a failure. And it's a reduction to a flow problem, and the graph is infinite. I will show you why the graph is infinite in 1 second. But before that, if you just plug into this 14.7 example that we had for peer-to-peer systems, even repairing a single failure naively costs you 7 megabytes network traffic. If you evaluate this bound, you'll find that you can repair with only 1.85. So there's a very large reduction in the communication required. Of course, there is one key problem that I don't know if you have seen already. I have not promised to you that this box is going to be exactly what is lost. I'm going to form here something that is a new linear equation that I only promise that any 7 out of these give you back the data, right? So this is much different than just having exactly x4 here. x4 was part of the data, but now I formed a new parity here. So I'm changing my code as I go. So that's one weakness of these results. Okay, now why do you want? Why is this graph infinite? So in general, you have your code here. Any 4 out of these, sorry, any k. This is general. So your file has size m. You cut it in k pieces. Each one is m over k in size, and this is alpha, the stored information. So when you have a failure here, you repair it by having a new node connecting to the existing nodes and communicating beta bits from each. Now you have repaired this failure, but now maybe there's another failure, and you repair it again, and then maybe there's another failure and you repair it again. So this graph is, you don't know which failures are going to happen, right? And these failures could be going on forever. So the graph here is unbounded in size, and you want to make sure that no matter when you connect to any k nodes throughout this infinite graph, you have enough flow. So you have to compute these parameters so that at any given time during this evolution process, there is enough flow on this infinite graph. So you have to find what is the trade-off between this beta, d, and alpha, the storage and the repair communication. Okay? So this is what we did. The punchline is, if you give me a little bit more storage, the repair bandwidth can be greatly reduced. So I'll just give you some numbers here. If you have a file that is, let's say, 20 megabytes, you cut it in 20 pieces, and you make 25 out of those, so that any 20 out of the 25 give you back your file. So you can tolerate 5 disks failing. If you use a Ritz-Solomon code, then each disk would store 1 megabyte, and each failure will cost you 20, because for repairing one failure, you need all the data. If you use what we call minimum storage regenerating codes, then you will be storing the same, but a repair will only require 4.8 megabytes. And the trade-off now was the following. OK, if you allow me to store a little more, so I'm going to inflate my storage, so each storage node stores 1.65, then you can you can compute these cut set bounds, and you will find that the repair bandwidth now is reduced to 1.65 also. So I increase my storage in the system by 60%, but my my repair bandwidth goes down 4 times. So, yeah.
Do you have any example, maybe later, of this reconstruction code? Is it just a linear code?
These are all linear network codes.
Okay.
The reason they are network codes is because to construct, to maintain them, you have to mix mixed packets. So I will show some examples in a second.
So it's just random coefficients and elements in a finite field.
Yes.
That's the only.
Yes. The thing is, if you do that, you are not going to have exact repair. You are going to be changing your code as you go. So your parities will be changing. They will be linear equations, but they will be different linear equations. And that is a big problem in practice. And the most exciting recent thing is how do you actually keep the code fixed? So I will talk about that in 1 second.
The goal is to reconstruct the file, right? So why is it a big problem if you can always reconstruct the file?
You can always reconstruct the file from any k. But most of the time, you don't want to, most of the time you want to just read one thing, right? So if you want to read a subset of the file, like you want to read one specific bit of the file, you don't have to get all k, solve these equations, and get to your data. You could ask for partial read, because most of the time you have 0 failures, and you just want to read something. So that's why it's always good to keep the half of the code uncoded. That's called systematic. So the half of the code is the data. Okay. Yeah.
Can you reduce by increasing the amount you store in each node, can you always reduce the amount of bandwidth to the exact size of the node?
Well, yes.
So the minimum,
yes.
If storage is not an issue, then bandwidth can be made as small as it is.
Yes. So there's an interesting point here. At this operation point, you communicate exactly what you store, which is the minimum possible. You see, because there's no way you could go below that, right? Because you're storing 1.65. And you can always achieve that, yes. So this, at the minimum bandwidth point, these two are equal. Yes. Okay, so there's a trade-off between storage and communication here. And the question is, what are the achievable points? So, okay, you can pose this as a graph problem. You have this infinite graph. Everybody connects to D, communicates beta. You want any data collector, so any k, to give you your data back. So choose these parameters so that everybody here gets enough flow. And this is the general theorem that I will spare you from the details. The general idea is if you have an n, k code, if you store alpha bits, you connect to D nodes and download D times beta, so D from each. So D times beta is gamma, that's the total communication. Then there is a crazy formula that describes the region, the trade-off region between communication and storage. Okay, and if I just plot it, it's much easier. So this is the region. This is how much you store per node. This is how much you repair totally, total communication. This point here is called the minimum storage point. So minimum storage regenerating codes stands for MSR. This is no coincidence, because we did half of this while I was here at Microsoft Research. So this is minimum storage point, and this is the minimum bandwidth point. So and there's a trade-off between the two. Everything above this blue line is achievable with random linear network coding, and everything below is information theoretically impossible by a cut set bound, like the one I showed. Okay, so this is all good, and this is going to appear, but there's one very important problem. So we characterize this region, but only if you're changing your code. So then if you talk to a practitioner, you say, okay, that's all nice, but I actually want to repair exactly what I lost. Okay? So this looks like a trivial extension initially, right? So you say, okay, now I lost this guy, and here I want to create a packet that is not just any linear combination that's in general position, but I want to repair exactly what I lost. And I have these bounds that were the cut set bounds. And now I want to ask, okay, this is a strictly harder problem. can I achieve the same cut set bounds, right? This was the open problem. And this is a very, very hard problem because, as I said before, when we reduce this problem to a network coding problem, you only have these data collector guys who want all the data. Now, when all your clients want all the data, this is called a multicasting problem, and there is all multicasting problems have been characterized, and they're easy to characterize. You only have to serve the poorest, and everybody else will get the information. However, now, when we have exact repair, we have these intermediate guys who want data themselves. They want specific linear combinations. So that problem, so this is the picture. Repair is multicasting, but exact repair is multicasting with intermediate nodes having requests. And the requests are overlapping. So different people might want stuff that overlaps. And therefore, the cut set region, the region I showed you before, the blue line, might not be achievable. Linear codes might not suffice. And we don't know, basically, it's a very, very difficult problem. If you have network coding with multiple sources, we have crazy examples of codes not, linear codes not sufficing, and we don't know how to characterize the region. So this was a very difficult problem, and it was open for a few years. Let me tell you the story. So in general, the question is, this is a blue region. What can you achieve with exact repair? OK, so the 2 points that we will mainly focus on is this point and this point. There are no results, as far as I know, for any intermediate points. The intermediate region is open. But let's look only at this point, basically. So these 2 points have received some work. The minimum storage point here and the minimum bandwidth point. OK. So for starting with Yunan Hu, when I was an intern here, we had this paper that said if k is equal to 2, so the original file size, you separate the file in 2 pieces, then systematic or exact repair. Systematic repair is exact repair. It's the same thing. You can match the cut set bound if k equals 2. So we had the constructions, codes, linear codes that achieved the cut set bound for this case. And then when I was a postdoc at Caltech, we were trying to find 5.3. This was the smallest case that was open. And Dan Kulina, who was an undergraduate at the time, ran a huge computer search over all possible codes, and there were some optimizations how to make this feasible. And we could find some codes that were 5.3 exact, so they were matching cut set for this case. And then there were some results by these 2 groups that show that if the rate of the code is less than 1/2, then exact repair can match the cut set bound. So this generalizes this result, but not necessarily this one. But they have very specific code. So they have to, your error correcting code has to be constructed in a very special way from these Cauchy matrices. And then they showed that you can actually repair these codes exactly as long as your rate below 1/2, and you could match the point on the blue curve, the cut set point. Are these clear what I'm saying? Okay. And one obvious question is for high rates, what can you do? So Kadambe, Jafar Maleki showed, and independently Shuramachandran showed that you can actually approach, not match, approach the cut set bound for any n, k for the minimum storage point using this technique that's called the symbol extension technique. And that's quite remarkable because this technique was developed for an entirely different problem, the interference channel in wireless, which has nothing to do with network coding, nothing to do with wired networks. It's a problem over the reals with wireless channels interfering. But exactly the same technique can be applied, and they show that you can approach the cut set bound for all k and n. So this is quite a remarkable result. The problem is that it requires an enormous field size and enormous subpacketization. So you remember I was cutting every packet in 2. Now you have to cut every packet, in 10,000 or billions, depending. It's exponential in n and k. So, but it shows it's possible. It can be done. So linear codes suffice to approach the cut set region for exact repair. for the whole range of parameters for the minimum storage point. Okay, so this is one point where we know we can approach it. Okay, so now I want to give you how much time do I have in general? I should have quite a lot of time, right? Half an hour. Okay, good. So since most people are still awake, I'm going to give you my 10-minute crash course on interference alignment and why this thing, how it's possible to achieve these results. Okay, so what's happening here? Imagine I give you 3 linear equations in 4 variables. Okay, in general, if I give you 3 equations in 4 variables, in 4 unknowns, you cannot solve for any of the variables, right? You would hope to solve for 3 of them, and if the equations were trivial, if the equations were A1 is 5, A2 is 11, and A3 is 12, then 3 equations in 3 unknowns, you get them. Okay, but now I have 3 equations, 4 unknowns. Okay, in general, you cannot recover anything from them. The only thing you can recover is that they lie on a subspace. Well, okay, let's look at these 3 equations. This is 3 linear equations in 4 unknowns. However, as you can probably see, I can use these 3 equations. So this equation says b1 plus b2 is y3. I can subtract this equation from these 2 and get 2 linear equations in a1 and a2. And I can solve for a1 and a2, right? So this is 3 equations that in 4 unknowns, but I can solve for 2 of them. Why? Because these coefficients here and these coefficients here are aligned. That means basically that the rank of this matrix, this is 1, 1, 1, 1, the rank of this matrix is only 1. And therefore, I can just get this one equation and cancel this interference and get 2 linear equations in the 2 things I actually want and recover them. Do you see what I'm trying to say here? Okay. So this is of course something you can do in high school. The difficult thing is how do you do many of these alignments at the same time? So how do we form good codes that have these crazy alignments, a lot of them at the same time? This is really the question. So here is my example of a 4,2 code that is exactly repairable. Okay, so this is what you were asked before. Okay, so this is first of all observe this is a systematic code. The first 2 parities are the data themselves. Okay, these are linear equations. A box now, a node stores 2 linear equations. Observe that any 2 nodes contain 4 equations that you can solve for your 4 variables. Okay, so this is indeed the 4,2 code. Any 2 boxes give you back all your data. Okay, now you lose one. What am I allowed to do? I'm allowed to send 1 linear equation from each of these guys to this. This is the newcomer. The newcomer wants to solve for x1, x2. What I'm allowed to choose is my coefficients here. These we'll call repair coefficients. So for example, I can do 1 times x3 plus 1 times x4, and I form this linear equation. The size of this is half a meg. I can choose these coefficients here again and form another equation that has half a meg and another equation here. I can choose these to any way I like, right? This is my choice. Okay, what are these now? This is 3 linear equations in 4 variables. There is no way I can make these equations contain only 3 variables because this has to be a good code. So there's no way I can choose my coefficients to only have the stuff that this guy wants. This guy wants x1 and x2 here. He really doesn't want x3 and x4. That's why this is red. So x3 and x4 is interference to our friend here. But the question is, I can choose 1, 1 here, 1, 1 here, and 2 inverse and 3 inverse here, so that the interference part is the same here and here. And then using this equation, this is exactly the same equations as the ones I had before. I can cancel this stuff out, and this guy now has 2 equations in the 2 things he wants. So is an example clear? Okay. So the interesting thing is that this code, if you lose the first node, you can do this. If you lose the second node, you can choose again different coefficients to repair exactly. And now if you lose this parity, now you have to recover this specific parity, right? Well, again, you can choose the coefficients, so you can solve for these linear equations and for these two. So this code is a 4,2 exactly repairable code, and it matches the 1.5 bound. So this was the construction that we had before, but this is not generalizable construction. Okay. So, and then there was this symbol extension idea of showing how you could actually generalize this. So first of all, before I want to go from this example into matrices. So how am I doing that? Well, okay, the first thing is x1, x2. So imagine multiplying by a vector here that is x1, x2, x3, x4, and this is the first equation. This is the second equation. And you know, the third equation here is x1 plus x3. x1 plus x3 is this row here. So this is my code. You can represent the code by its coefficients in this form. The repair coefficients are these things that are sitting here. What is happening in the previous example is that this is the interference part. This is this x3 plus x4. And the key is that this matrix has low rank. This submatrix here has rank 1. And I get this extra equation on x3 and x4, and I can cancel these two and get a full rank matrix on these. Okay, this is really what happened before. All right, let's look at it more abstractly now. This is the systematic part. These are the diagonal ones. Now this is the general code. I can choose any code I want, and I can choose any repair coefficients I want. In fact, I chose different repair coefficients here and here, but the Kadambe et al. Scheme uses the same coefficients. So I'm going to restrict my freedom and choose the same coefficients here, and choose the same coefficients for all the systematic blocks. So that's one assumption. I'm going to form all these matrices. What is my goal here? So choose the same V prime for all systematic, the same V for all non-systematic. And they also chose the matrices to be IID diagonal. Okay? This is their choice. They can do whatever they want with the matrices. So they chose the matrices to be IID diagonal. Okay, what is the requirement? The requirement is that all these things here are contained in this small matrix, so I can cancel. And at the same time, all this stuff here is full rank, so I can get the stuff I actually want. All right. Now, how am I going to do that? That's actually a very difficult problem when there's many matrices. All right, so I say we want this full rank, and we want these vectors to be in the span of these. All right, so we have to choose V and V prime because we already chose these matrices A. In general, I could choose the matrices A and the V, right? But these are quadratic equations that I cannot solve. But they set A's, so now I have to choose the V's. Okay, so this is my one slide crash course on this symbol extension thing. Okay, let's start by choosing V prime here. Let's start by choosing V to be one vector. Sorry, not V prime, V. So let's say this was one vector, only one vector. Well, if this was one vector, what do I need? I need V prime to contain V times this matrix and V times this matrix. Okay, that's two extra vectors. So if I chose V to be this, then V prime would have to be these three vectors, right? The blue here is the extra stuff, the suboptimal stuff. Ideally, if I was operating at the cut-set bound, there would be no blue stuff. But now, when I start from one vector, after mapping it, I get 3. Okay, that's a lot of overhead. It's a huge overhead. But now I'm going to do the following thing. I'm going to say, okay, now I'm going to take this and pretend this was V. So I call this fold back V prime into V. So if V was this vector, these three vectors now, well, now I would have to make sure that every vector multiplied by A32 and A42 would stay invariant. Now, I multiply again by A, and I get these 6 vectors. So observe now I have some overlap, because W times A is already in here, and W times A squared is not, but in the next step, I'm going to fold it back in. I'm going to have more overlap. Okay? So this is how this construction is working. And if you now you pretend this is V, and you see what would V prime have to be, and you keep on doing that, you will see that the blue stuff, the extra stuff I have to get to cancel, is actually a vanishing fraction of the overlap. So almost everything is aligned, and the part that is not aligned is vanishing as I keep on doing this process. Now, why is that a problem? What is the problem with that? The problem is that until this becomes very small, I have to make this a very large number of equations. So this is the general statement that says if you use this idea of folding your equations back again and again, you get perfect alignment. But to get close to perfect, you actually never get perfect alignment. You get super close to perfect alignment. But to get super close to perfect alignment, you need a ridiculous number of these foldings, exponential number. Can you do it better? I don't know, and I think nobody knows. And this is like the million-dollar question. In how can you do this without extending your field so much, without cutting it into so many small vectors? Okay. But this shows that linear code suffice to approach the cut set region for exact repair. This is for the minimum storage point, of course. For the other points in the trade-off, we don't know again. It's only for one more point we do know. But for the region, we don't. Okay. And the key question is, do it with small field and small subpacketization. Okay. So some other new results. So this technique was done for the wireless interference channel, right? It's a completely different problem. So this surprising result we had is the following. If you give me a code, I choose the repair coefficients that reduce the repair communication over a field. This is a computational problem. If you give me a fixed code, this is a computational problem. It's NP-hard. It's a rank minimization problem over a finite field. This is another problem. You give me channel matrices in the wireless interference channel, and I have to choose the beam-forming matrices that maximize the degrees of freedom of that wireless interference channel. So the one result that we established recently with my student is that both of these problems are basically the same problem. Basically, if you had the box that could solve one, you could use the box to solve the other. But of course, this is over a field. This is over the reals. But the problem is essentially the same. It's minimizing the rank of some matrices subject to the rank of some other matrices being full. Like I think you can see that for the repair case. For the interference channel, it's another story, but it's very simple. So these problems are connected, and there is other problems that can be put into that framework. So, for example, you can think of security and secrecy problems where I want to communicate to some guys, and I want other guys to do not get anything. Again, that you can pose as a problem. I want full rank at this receiver, and I want 0 or 1 rank 1 at the bad guys. So this is one problem is, for example, the multiple access channel with eavesdroppers. And there, using the interference alignment technique, we can find the secure degrees of freedom for that. So recently also, this was applied for the problem of multiple unicasts in network coding, probably the most important problem when you have multiple single source, single destination pairs. Again, you can apply interference alignment techniques, and you can show under some cases very good performance. And another area of open problems is, of course, I assumed now my topology was fixed, and everybody was distance 1 from every other, and I was counting bits, right? But instead, maybe there is cheap bits and there's expensive bits. There's some people who are close by and some people who are far away, and maybe you want to get more bits from some people and a fewer number from others. So what's the right repair if you have a given topology with costs? That is one open problem. There was one paper by Bao-Chun Li and his group at Infocom recently on that, on repairing on trees. And I'm going to talk about allocations now. How much time do I have? Maybe 15 or 10 or Well, 10? Okay. So before I move to that, are there any questions on repair problems before I move to the slightly different? Yes.
Is there no loss of generality in that in between reals and fields? Like suppose I solve the repair problem over reals. There are some like with finite number of bits.
Yeah.
Like some packetization or something. Do you think it can automatically, because you had that equivalence? Right?
No, I said if I had the box that could solve both. If I had the box that could minimize the rank over both. Yeah, so something like that. Yeah.
So that's the real question, whether that box is the same.
Yeah. So we don't know of any scheme that works in one and does not work in the other. Of course, I would expect if you limit my field size, so if you limit my field size to be binary, then of course I have much more restricted. So I mean, we don't even know the repair bandwidth for binary, even for functional repair. So bounding the field size is also a very difficult problem. But all the techniques that work for reals, for some reason, so far work for, right? So it's, yeah, I don't know. Any other question? Okay, let me move on to this allocations, and then there will be more. All right. So this is just a motivating slide that says that everybody's watching videos on their iPhones, and that's a huge problem because 3G cannot tolerate that. And what are we going to do, right? And you know, you can put more antennas, but this is not going to scale in the right way. And the key approach, I think, is to do delivery of content with opportunistic contacts. So, you know, use some idea like femtocells or even device-to-device communication to cache content and give the content in a device-to-device way, rather than getting it from the server using 3G. Okay, what is the point of this slide? Basically, the video you want to watch is very likely to be downloaded by someone nearby in the near future or past. I claim this. This is not always true. Depends where you are, but in many cases it is true. This is one of those plots that shows, you know, 10% of the content is responsible for 90% of the traffic on YouTube and everywhere else. And this is the other interesting thing, that storage is increasing more than anything else. Storage in phones is increasing more than anything else, and storage in, you know, in boxes is increasing extremely. So you can have a lot of storage. So the idea is, can you do distributed storage of the popular content and deliver it to the mobiles in a device-to-device or a localized way? Okay. So there's a lot of open problems here. Okay. So let me tell you a few of them. So again, of course, you might want to use coding instead of replication. You might want to code across the content rather than just store the content in different storage nodes. And if you have again the problem of maintaining the code, and all these regenerating code stuff is relevant here. But there's also many other problems. So you would like nodes to cache different content in a distributed way. So you don't want everybody to cache the latest Lady Gaga video, and then the second latest Lady Gaga video is nowhere to be found. So we have to coordinate about what we cache. And we have to find a way to cache the popular content, but in a somewhat balanced way. So which content to cache is one question. How much to store? This is almost the most basic question. How much to store on each of the storage nodes? How to find who has the stuff I want is another question. And how do you give incentives maybe to people to donate their storage and their resources? Maybe in a BitTorrent way, you will get faster. Yes?
Going to be over Wi-Fi?
You could do it over Wi-Fi. You could actually do it over 3G.
No, but then it's the same bottleneck.
No. You could do phone device to device over 3G. So I mean that would require. I mean it's technologically very feasible. It is not done in current technology, but so you could talk over different models. The key point is you want to limit your power. So you want to go to the model where I talk very quietly in a very small radius. So any technology that will allow that. So So these are all very relevant problems for this. I'm going to just mention the most trivial one. Okay, so I'm going to mention a very trivial problem: how much to store. So for example, I have 2 files, and I want to store them in 5 storage nodes. One thing you could do is you could say, okay, I'm going to store the first file in the first 2 nodes and the second file in the second. But you know, and then somebody's going to drive by and with some probability access each one of these. Okay, that's one storage scheme. But you could take the first file, cut it into pieces, and code. So any 2 out of the orange give you the yellow file. Any 2 out of these give you the blue file, and then store this. Now, any 2 storage nodes contain both files. Okay? So this is, again, a strictly better storage than using replication. So you might want to code across your storage devices and get better access to your content. This is what I want to say here. Okay. But you could also change the allocation. So maybe you store both files at the first guy, both files at the second guy, and you leave these guys empty. And by empty, I mean you store other stuff there. Okay. So this is a different allocation. Was that a question? Okay. So this is a different allocation. So which allocation is better? Well, you say, okay, this one is better, obviously, right? You know that, but that's not clear. So I'm going to make an even more trivial problem. My most trivial problem is I have 1 file to store, and each one of my storage devices is going to be like a bucket, and each of my buckets is going to be killed with some probability independently, the same probability. So every device will be crushed with probability 0.1. I have a fixed redundancy of 2 liters of water, let's say, and I have used the code. So any 1 liter out of these 2 gives me back my file. What's the best way to allocate my redundancy in these 5 symmetric storage devices, right? That's like the most basic thing in the world. And I have like 5 minutes, maybe? Okay, well, basic. Okay, rough, give or take. All right, so this is the most basic thing in the world, right? Okay, so let me give you an example. So you have your fixed storage budget. So you're going to allow two units of storage. So one thing you could do is this. 1, and leave the others empty for another file. So we call this minimum spreading. The other extreme is maximal spreading. Spread your budget equally overall. And maybe you could do this, right? Maybe you could do 1/2, 1/2, 1/2, and empty. Okay, so when somebody told me this problem a while ago, I said, okay, you know, everybody knows that's the best thing to do. That's the most reliable thing. Turns out it is not. And okay, well, I said, okay, maybe if the probabilities are different. Let's say, no, but even if the probabilities are the same and everybody fails independently, this is not always the most reliable thing. Okay, why? You just look at, you just play with some examples. What's the problem? Maximize the probability that the sum of the xi's that survive, so this is indicators, is greater than 1. So if it's greater than 1, my code suffices to recover the data. If it's smaller than 1, even if it's 0.99, I get nothing, right? Because from a code, unless you do something clever, you get nothing. Subject to the total storage is less than your budget T. Okay. And of course, you can generalize to different failure models. And this is non-convex and harder than it looks. So this is what I want to tell you. Even this very basic allocation problem, we don't know how to solve. Why? Okay. So first claim, symmetric allocations can be suboptimal. What do I mean? Let's say you give me 5 storage nodes and you give me this budget, 12/5. That's my total storage. You can prove that this crazy allocation that is not symmetric, so it's 3/5, 3/5, 2/5, 2/5, 2/5, is better than anything else. This is the best way to allocate information. If you restrict yourself within symmetric allocations, which means they are all the same or 0, the best symmetric allocation is not to store evenly on all the nodes, but to store evenly on 4 and leave the 5th guy empty. Why? Because now 2 nodes contain enough information to get 1 unit, whereas if you were spreading evenly over all of them, you would need 3 nodes to get 1. So finding the optimal allocation is very difficult. We don't know how to do. Finding even the optimal symmetric allocation is non-trivial. I mean, of course, you can check, but we don't have a closed form for even the best symmetric allocation. So this problem has been discussed. It was discussed at Berkeley by several people for a while, and in general, it is open. Do you understand the problem? Is the problem clear? Okay. So I can tell you a few intermediate results that we had on this. Okay, so for the IID model, we proved the following thing. Maximal spreading, which is spread the intuitive thing to do, maximally spread the eggs as much as you can, is optimal. It's not optimal. It is asymptotically zero gap from optimal. So the gap from an upper bound vanishes if you are in the regime where TP is greater than 1. So T is the budget, P is the probability of success. TP is the expected amount of bits that will survive in the system. And if under this condition, then this is an allocation that approaches optimality as n grows. This is the only result we have right now. I mean, we have other results for symmetric allocations, but for the best allocation, it's quite challenging. So this will appear in GlobeCom. Okay, so even for storing one thing, what's the best way to allocate is highly non-trivial. That's what I wanted to say. Other problems, repair problems are, of course, very difficult under errors. So if you have incorrect linear equations, if somebody introduces incorrect linear equations into your code, then these equations will poison everything else afterwards, right? That's a big problem with combining stuff. If some of your equations are wrong, even if the guy leaves, now you repair this other guy, you get poisoned equations. Your whole system will get poisoned, even if one linear equation is incorrect. So how do you deal with that? You need codes that can tolerate errors. So now how do we repair codes that can tolerate errors? Or how do we use some hash, some signature scheme, and all these are very interesting. Okay, so I will conclude. Before I conclude, I actually maintain a wiki of the bibliography on storage stuff. So if anyone is interested, they can go there and see there's like a lot of literature for the repair problem and the allocation problem and a few other things. So if anyone is interested, you can find it on my page. Okay, a few open problems. So cut set bounds are tight. We don't know. We only know for a few points. And are there practical codes that can achieve them? This is, of course, a relevant problem. What is the limit of interference alignment techniques is a very fascinating question for network coding. I think actually interference alignment is more useful for network coding than for wireless, because for wireless you have to assume you know the channels perfectly, and whereas for network coding you actually can do what you want by yourself. You design the problem. Repairing codes in small fields, as we discussed, is very tricky and interesting. Repairing existing codes that people have already deployed is a very relevant problem. So for example, the B-Code and EVENODD are useful codes that are used in RAID systems. How do you repair those given codes? And we have some preliminary work on that. How do you deal with bit errors in security? There's a paper on security that appeared in ICIT. And finally, what is the role of non-trivial network topologies, as I mentioned? And last one, allocations, even if you have multiple objects, is the real problem, and it's highly non-trivial because even for one, we don't know what the optimal thing is. So I think I will stop here, and any questions will be welcome. Yeah.
The interference alignment seemed to. I mean, there must be some special structure of the problem of the exact repair that makes it possible to achieve the same capacity region.
Yeah.
Is that? I mean, because in light of the other results of Daugherty and Seeger and so forth, it seems that in general you can't do as well.
Yeah.
So, do you have any sense of what that special structure is, and what kinds of networks these tricks will work?
It's a very good question. So so far all the networks that I know are reduced to these rank minimization subject to full rank constraints. So I can write repair as an optimization problem of choosing these repair coefficients to minimize rank of some matrices, say some of the ranks, subject to some other matrices being full rank. And interference alignment for the wireless channel for the wireless interference channel, I can write again in the same fashion. Now, I cannot write every network coding problem in that fashion. So this is, but it is a fairly general framework. I do not know if this, so there's many techniques for interference alignment, but the symbol extension is the technique that actually achieves the cut-set bound asymptotically. For example, we don't even know if this technique achieves the cut-set bound for the intermediate points, because we have shown it achieves it for the minimum storage point. So the intermediate points, for example, is unclear if so. The minimum storage point is a very interesting point, probably the most, because it corresponds to MDS codes. So it corresponds to people using Reed-Solomon, and so it's exactly the same point. I don't know what is the magical structural property that allows it, but the fact that it was used for multiple unicasts also shows me that it's very wide. It's not just the interference and the repair. It seems to be more general. Yeah.
Fascinating, topic, and thanks for very good work and interesting talk. For the spreading code, which you discuss later, have you considered that with the interference alignment? And any intuitions on that?
Well, no, because I have not. You mean the allocation problems? I have not. I have not tried to apply any. Well, one interesting question there is if someone gets a smaller subset of the equations. So, for example, there are some users that get k equations, and some users get, let's say, k over 2. In general, if you have an MDS code, any k will give you all the data, but k over 2 will give you nothing. So the problem with the reason this allocation problem is difficult is if you get 0.99% of water, you get zero useful information.
I think here is this. Basically, this allocation problem generally target data survival. So basically, let's say I have data I want to store in the systems. I want to make sure the whole copy of the data is safe in the storage, right? But the systematic property of the code is important for data retrieval.
Right.
So many times when you want data, you may not want the whole data.
Right.
You just may want basically a piece. And the systematic basic property will just make the retrieval much more efficient.
Right.
So I think these two properties is indeed very desirable in the storage system. And ideally, you want them both.
Yeah, I see. So basically, you're saying that okay, that's a very good point. So the reason the allocation problem is hard is exactly this hard all or nothing. It's this all or nothing that makes it hard, because I say the probability that I get 1, if I get 1, I get all the data. If I get 0.99, I get nothing, right? So that's a step function that is you're trying to optimize. That's why it's so difficult. If I had a softer function here, so if I said, okay, if you get 99, you still get some utility, then this problem would become easier. But now the question is, how do you design codes that have good, graceful degradation? Of course, as you said, a systematic MDS code has some graceful degradation. But is that the best thing you can do? I don't know, for example. And then you could use interference alignment for that.
I think basically my point is for practical reasons. I would rather have a systematic code,
of course,
non-optimal, than an optimal code, but not systematic.
But I believe that a systematic code is also optimal for graceful, in terms of graceful degradation. I don't think you can do anything better than keeping some bits in the clear and then some parities. So I think actually that practically, of course, I agree with you, but I think even in theory, it is the best thing you can do. So and perhaps you can use alignment for that, because that is an alignment type of a problem. It's a very good point. Yeah.
For this resource allocation problem, you presented it like it is water. But what do you think about using coding that is not treating it as water but treating it as coding? Do you think it helps? Or?
Well, coding makes it water because So I'm thinking of taking the data and multiplying by a full matrix that is random IID and n by k matrix. Okay. So any k will give me back all my data. So that's why any 1 liter of water gives me back my original liter of water, right? So and then of course I'm saying, okay, I make the packet super small so I don't have to worry about the discreteness of the packet. But as we were saying, if you had some graceful degradation, then the problem would be different, because then I don't just want this. I want to maximize some utility which depends on the surviving amount of water. And then, if I had a very simple objective function here, maximize the amount of water, just the amount of water, then it's trivial. So but that's not going to be, if you had the magical code that any k gave you the original data and any k minus 1 gave you k minus 1 of the data and any k over 2 gave you k over 2 of the data, then this would be a trivial problem. But I do not think, of course, that this is possible. And what is the best thing you can achieve with a code that performs well at 2 points or many points is a very good point. I conjecture that the best code is the systematic one. So a systematic MDS code is performing, I don't think you can beat that, actually, with any other scheme.
All right. Thank the speaker again.